I'll be posting these notes that you see up on the board. Most of it's going to be just in my handwritten notes. You'll see that on Moodle. And then most of the time, every time I'm successful at recording it, I'll put the recordings on there too, so you can go back and so that would make a difference in your note-taking in the sense that you can focus on, more what's being said and how that's connecting in with what you're seeing, rather than just your notes being just what's on the screen. So, like, you can, make your note to yourself in parentheses like other stuff if there's stuff that you need to refer to from the original notes and work around, some of the things that I'm saying rather than just copying what's written down. Okay, so think a little differently about how you take notes in this class. Okay, so for the first thing you see, there's a list of 5 different properties. We're going to talk about a few more. It's not important to understand or to remember the formal names of these things. Like, that's not going to be a question on a test saying, what's the associative property of addition? That's not the point of this. What I want to do is give you examples, and the examples that, or the way I show you how these rules operate, that's the thing to remember. It's just what are the legal and permitted operations that you can do algebraically, not can you categorize everyone into some name that is using words that we don't normally use in conversation. So what the commutative property is about is that we can add things, and I think I have a little difference here. Yeah, like that. Commutative property means that we can add things in a different order. So 5 plus 3 equals 3 plus 5. It's almost intuitive, but there are actually operations in math that aren't commutative, like division is not commutative, for instance. If you say 5 divided by 3 is not the same as 3 divided by 5. So, but addition is one of those things that it does commute, that we can change the order in which some things are written. And then the commutative property of multiplication, we can do this with multiplication as well. Now, sometimes the meaning is slightly different, and here I go A times B and B, C again, so maybe I changed it. I did. Good. Having 3 columns by 4 rows is a little different than 4 columns by 3 rows. You end up with 12 both ways, but the meaning is slightly different. And so numerically these things commute, but remember that there might be a meaning with the units that are involved that have a slightly different meaning, even though you may end up with the same numerical result. Okay, the associative property. What this means basically is that if you have numbers that you're adding together, it doesn't really matter what order you add them in. So combining the associative and commutative properties, when you have a list of numbers to add, so long as you make sure you get all of them, you add them in any particular convenient order. And so we'll see this when we're adding polynomials. We'll add terms out of order and things of that sort. But it works fairly simply this way. And then also multiplication commute is associative as well. So 2 times 3 times 4 is the same thing as 2 times 3 times 4. In both cases you'll get 24. 6 times 4 versus 2 times 12, but still the answer is the same. Now there's what's called a distributive property, and here's one that may get a little confusing because it's really the distributive property of multiplication over addition. That means that I can distribute, when I'm multiplying a sum of 2 things, I can multiply those individual terms separately and then add them together. Like if I want to take a 3 times 2 plus 5, I can say 3 times 2 plus 3 times 5. Now when you have small numbers like this, obviously the easiest way to do it is it's just 3 times 7 rather than saying 6 plus 15, but we'll find that when we're dealing with variables and things that this is kind of a convenient property. The thing to remember is that you don't distribute multiplication over itself. What sometimes happens is you think when you have three things that you're multiplying, this is not the same thing as AB times AC. You know, this doesn't make sense. What we would do is you can take A times B, but then you just multiply by C. And so with multiplication, when we're multiplying factors, remember only to multiply it once, that you don't have to multiply everything by that. So, for example, if we have a 3xy, this does not equal 3 times x plus 3 times y, and it also does not equal 3 times x times 3 times y, because then we get 9 out of this thing. So this is a point to be careful in, and it may seem obvious with a simple example like this, but you'll find when we're dealing specifically, especially with polynomials where we're multiplying different terms together, you have to really think, okay, do I distribute here or do I not? And you distribute when you have multiplication distributing over a sum of things. Okay, a few more. The additive identitive property, this you probably just recognize that when you add 0 to something, it doesn't change. Okay, so the identity for addition is 0. The multiplicative identity is times 1. And in and of itself, these things don't really seem all that interesting, but what we're going to do at some point is we're going to take things like A times B over B, and really what we're saying is A times B over B, which is B over B is 1, and so we get A. You normally think of this as canceling, which is fine, but we're really using the multiplicative identity property when we so-called cancel with fractions. The additive inverse, I talked about this on Monday a little bit. The book sometimes calls it the opposite, that -5 is the opposite of 5. I'll be using the words inverse, additive inverse more because I think it's more precise. Opposite is a little confusing because it doesn't really say opposite in what respect, addition or multiplication. The multiplicative inverse property is that we have, if we take the reciprocal of something, we multiply it by 1 over that something and we get 1. And the exception is when that thing equals 0. 0 times 1 over 0 does not equal anything because 1 over 0 is undefined. And so this property, this is the first property that we see that only, I don't know why I did that. This is the first property that works with some restrictions. Okay. All right. Last few here, we have properties of equality, and what this means that if you have two things that equal each other, that means we can add the same thing to both sides, and we can multiply the same thing by both sides. And it works the other way around, that if something is added to both sides, we can subtract it from both sides, and if something is multiplied by both sides and that multiplicand is not 0, then we can say, you know, that the two things are equal. So that's a mouthful of words to really show you that if x equals y, then we can add 2 to both sides, or we can multiply both sides by 2. If it's the other way around, that if we have x plus 2 and y plus 2, x equals y. And so these are the normal manipulations you make when you're simplifying expressions, but it really is a formal property of equality. The only thing that we have to remember is that this relationship holds only when this number that we're multiplying, in this case 2, is not 0. So 0 times y equals 0 times x. That could be, but that doesn't mean that x equals y. Because 0 times 5 equals 0 times 2. Doesn't mean that 5 equals 2, right? Okay, and then properties of 0. 0 times anything is 0. 0 divided by a is 0. And remember, that's a perfectly good number, okay? A over 0 is undefined. And so, especially when we're dealing with some of these factors in polynomials, when you get 0 in the numerator and other things in the denominator, non-zero, that's a perfectly good value. That's not the same thing as when you get a 0 in the denominator. Okay, so normally this isn't an issue when you're just talking about numbers, 2 divided by 0 or 0 divided by 2, but it'll be a little bit more with some of the things that we see in the future to keep in mind that When something equals 0 in the numerator, that's a perfectly good 0. Properties of negation here. This is -1 times a equals -a. -1 times -a equals a. So you probably think of this more as properties of multiplication, which is true, but something like this, you know, wherever we get the negative, it still makes it negative. Wherever we have the negative, whether it's in the numerator or in the denominator, that makes the whole ratio negative. And there's no particular reason why one of these is better than the other. Generally, you would write this one in a simplified form, but you know, it's perfectly fine to leave the negative in the numerator or in the denominator. There's no magic about that. Okay, so those are the properties of real numbers, and hopefully that's all review. Don't worry about the names of them, but you know, the actual manipulations and the properties that they give you, you should be familiar with. Expressions. Okay, algebraic expressions. Define some terms. Hopefully nothing is incredibly new here. Variables. When we talk about variables, we're talking about a letter that represents a value. Okay, and we may know what that value is. We may declare that that value may be a part of a set of values or something of that sort. But variables, we normally use letters. And constants, what we're referring to is any real number, and it doesn't change. Okay, so we may say that a is a constant. Okay, so a in that case is both a variable because, you know, we perhaps don't know what it is, but we say that it's unchanging. You know, so if we say the expression y equals mx plus b, which is the equation of a line, m and b are constants. You know, in that context, and x and y are the variables. So when we have a polynomial expression like this, we're going to refer to each of these things that are added together as a term. So this is a 3-term polynomial. And the last one, since it doesn't have a variable in it, we'll call that the constant term. Now notice the negative sign rides along with it. So when we're talking about a polynomial with several terms, we're really talking about adding all these terms together, and the negative sign rides along with the term. It's part of the term. Okay, so think of it as separated by addition, negative sign, part of the term. Okay, and then what we call the number in front of the variables is the coefficient. And so the coefficient is allowed to be 0. Oftentimes when it is 0, we just simply don't write the term because the whole term is going to equal 0. But we're going to refer to those numbers as coefficients. Okay, so when we're simplifying expressions here, what we want to do is we want to collect like terms. Okay, this is the first thing. Simplifying, there's several ways to simplify, and we'll find that we won't always simplify to the same extent, but there's a few things that are universal about simplification. First one is that you want to collect the like terms. And what we mean by a like term is that they have the same exponent with the variables. So the same variable, same exponents. Okay, so notice we have a 2x cubed and an x cubed, so those are like terms. The negative 4x squared and the negative 2x squared, those are like terms. They have different coefficients, but they have the same variable, same exponents. And so we can add then add or subtract the coefficients to make this a simpler expression. So the 2 plus 1 equals 3, and then the negative 4 and negative 2 equal negative 6. And then the x, of course, is unchanged. So that's the first part of simplification, is to remember to collect those terms. Okay, next part is we're going to use all those properties of real numbers that I went through to remove grouping. And so what I mean by this is we're going to try and eliminate parentheses and brackets. And so The way that you should do this is work from the innermost parentheses first and simplify, and then keep on going to the outside. So in this case here, you look at the innermost parentheses, and that says x minus 8, and that can't be simplified. Those are not like terms. So then the next thing we would do, we would then multiply -4 times x minus 8. So one of the things that I want to encourage you to do is do a lot of writing. Okay, one of the things that a lot of people feel like is that the less they write, the faster they're working. And so let's say you're doing your homework or you're taking a test and you have an expression like this to simplify. It's usually because you stop and think, and you think, okay, with the negative, that -4 times -8, you know, you're trying to reconcile a whole bunch of things and write it all down at once. Do one thing at a time. And there's no penalty for writing too much. In fact, it's a good thing to write a lot because you can go back and check your work more easily, but you also make fewer mistakes by doing so. And so if there's one thing you can do to a problem, do it. And then the problem changes a little bit, then perhaps there's one more thing you can do to it. So it does help you kind of work through. So the first thing I'm going to do is multiply through that -4, and I get -4x plus 32. And then I'm going to combine like terms. Now notice what I did here. I didn't distribute the 3. I didn't get too excited about, okay, now I can distribute this 3. I'm looking at my terms, and I say 2x minus 4x. And so I'm going to actually write that down and not think about it. I'll write it down. So now I have a simple problem. It's simply a 3 times these two terms in here. And then we get -6 plus 96. Okay, so these things, they look simple when you're watching them, but when you are actually doing them, you know, it takes a certain amount of concentration not to get tripped up by the fact that you have a lot of things to do. So make your problems simpler by doing one step at a time, and you'll be more accurate that way. Okay, and we'll have some practice with this, but evaluating expressions now. Actually, before we go there, let me write one on the board just to give you some practice on simplifying those expressions with parentheses. Okay, why don't you try that and do these one step at a time. And I think, you know, by writing, you should be writing, let me see, 1, 2, at least 3 or 4 lines to do this. Don't try and do this all in one line in your head. Okay, anybody get anything? Somebody want to walk me through? Tell me step by step what you did, okay?
First I did parentheses in the brackets.
Okay. So what did you get?
Negative 21 and negative 3x plus 32x minus 4x squared.
Good, okay.
And then I combined like terms,
Okay,
and I got 34x minus 21 minus 4x squared.
okay.
And then I
Distributed?
yeah, distributed, and I got negative 68x plus 42 plus 8x squared.
Good. Okay, everybody get that? Now, it's okay at some point in here when you get to this point or this point, you know, the traditional order, and we haven't started talking about polynomials though, but the traditional order is you go in decreasing degree with the terms in there, but that's not so important here. What's important is that all the terms were collected. So there's four lines of writing, and you know, one of the things that I've found with students is that, especially when you're taking a test, the time goes by on a test when you're thinking. When you're writing is kind of like free time. And so by writing one line at a time, you're going to get to the end of this problem a lot faster than if you think about how does all this combine and try and, let's say, cross over from this step to this step, or go right from here to here, to say, okay, I could take -2 and let me see, I'm going to have a 2x and a 32x, you know, and try and do the multiplication and addition at the same time. You're really going to be a whole lot faster and more reliable if you just do one thing. And also it makes what looks like a hard problem a whole lot simpler just by writing things out, because you only have to concentrate on doing one thing. Okay, so evaluating expressions. When we evaluate something like this, keeping track of the negative signs is probably the biggest challenge of these, all right? We want to plug in a -1 wherever we have x, and a -2 wherever we have a y. And so I think writing this out, so wherever you have the variable, put parentheses and drop the number right in. Don't try and reconcile all the signs yet. Like when, okay, the top one will be easy enough because that's going to be -2, and then we have a -1 where the x is. But then you have to think, okay, -y and y equals -2, so that makes a +2, and then you have to add that. You're going to get there, you know, but just for the first step, just simply, mindlessly, write parentheses, drop in the number. Okay, so there's an operation that's reliable, it's easy, you don't have to think too much, you just have to make sure that what you're putting in the parentheses for x is x, and what you put in the parentheses for y is y. And then you can go on, and now you have a simpler problem because you know how the negatives are going to reconcile here. You can keep track of this one, you can keep track of that one. And so in 2 more steps, I didn't try and do this in my head, I just wrote out, first simplified all the signs, and then I simplified the expressions, and then I did one more reduction. So it's fast that way, and it's reliable. Okay, so that one is, so that's that. Is we want to construct algebraic expressions. And so here we're going to kind of make the connection between what a natural language, what plain English is, and what we want to do in terms of having expressions that we can manipulate mathematically. Okay, so translating ordinary language is what it's all about. And so the thing that we want to do is you want to look for keywords in operations. And this is admittedly not the easiest thing to do always, because some of the words imply a change of order, and some words, just naturally translate into symbols, like the word is easily translated into equals. You want to use, of course, variables and numbers to represent what the things in the natural language are. But one of the things that you should do is maybe take an extra step and actually write out what the definitions of the variables that you're using. And I'll show you some examples of that. And then look at the verbs, and that usually establishes the relationships. Is usually equal, but then you have verbs that say added to, or things of that sort that convey some sort of meaning that puts on some relationships. Okay, so let's look at this particular one. The pencil is 20 cents more than the pen. All right, so how do we do this? Now, we could say, all right, what do you want to use? What variables do you want to use? And how do you want to convey that? So I'm going to first write out what I think are good variable definitions. So I'm going to define C as the pencil cost, and I'm going to use P as the cost of the pen. Now, normally it would be kind of nice just to use the first letter, but we have two words that start with P, so I've decided to put P in with the cost of the pen, and so it's a distinction that I've written down. And that's a really important thing. Okay, is your verb, and so there's an equal sign, and then you have 20 cents is written in the traditional way of writing 20 cents, and then more than the pen, so 20 cents more than the pen. You see how that's 0.2 plus the cost of the pen. So you don't worry about which side do you put the 20 on or whatever. This one is a literal translation, and it flows pretty naturally. One of the things that if you're not sure that you're putting it in right, what you can do is just do a little thought experiment. Okay, so if I say my brother's 5 years older than me, okay, so what does that mean? Actually, my brother's 5 years younger than me. Okay, so my brother Carl, that is. And so I think, okay, if I'm, when I was 10, he was 5, and start thinking about, once you write your equation, to put in a small example to see, does this make sense? Does it do what you want it to do? And so I'm going to be kind of fussy about this, defining the variables. You might see, you do some nice work and everything, and if you translated it from a paragraph or something, I will ask, what is P, what is C, what is X? Now we use a lot of X and Y's in algebra, and that's all well and good. That's what the tradition is. That generally means just any old real number. When you're translating ordinary language into algebraic language, use variables that have some meaning. P for pen, or C for cost, or any of those things. Like if you have the kind of problem that has names in there, Bill, Ted, and Alice, B, T, and A, as your variables. It just makes it a lot easier to remember as you're going through and see, are these things reasonable? Okay. So this just translates simply into C equals 0.2 plus P. Okay, so here's some keywords and phrases. I'll just let this all spin out here. Whoops, that's too much. So when we talk about addition, you usually see the words plus, some, greater than. Subtraction, you'll see minus, less than, difference, and that sort of thing. Multiplication has some kind of weird words sometimes in there, with product and times and twice. And the other one that you see oftentimes that implies multiplication is of. Okay, O-V, O-F, I mean. Can't spell. I'm a mathematician. I'm not anyway, when you say, 3 of those is really 3 times that, right? Like you say, I want when you think about those kinds of expressions, when you say of, you're talking about multiplication, never addition, right? You're always talking about whatever quantity you specify times whatever quantity you're looking at. So we'll see some examples. Now division gets a little tricky because you have things like quotient, ratio, and per is a really good one, you know, like what's the cost of those? Well, it's $1 per 1,000, or you know, something of that sort. What that implies is division. So order is really important with division, especially because that's the one that's not commutative. All right, which one is the numerator and which one is the denominator? You have to be very careful when you're reading. Okay, so part of your homework is I want you to find 3 more of these that are not in the book and given as an example using each. Okay, so I'll repeat this on the homework that I write, but what I'm really interested in is you're going to come up with 9 new words that seem to infer addition, not 9, 12, that seem to infer addition, subtraction, multiplication, and division. And it'll be a little bit of a challenge, but you can go kind of mining for these if you want. Look through your book and look for word problems, not that you'll necessarily be able to do all of them, or it's even important to do all of them, but look for the words that may suggest either addition, subtraction, multiplication, and just about every sentence in a word problem will convey something like that, so you can get through those. So the ones that, you know, I gave you 3 of each: sum plus greater, minus less than difference, product times twice, that kind of thing. You should be able to find 3 of each as an example. All right, so onward. Defining variables. All right, you can use any letter, and use a letter that reminds you of what the variable is. That's just a nice habit to be in. Now we only have 26 letters, and not that you're going to do problems with more than 26 variables, but sometimes, you know, like in that example I just gave, P is logically 2 different variables, so you have to define, you know, 2 different letters for them. And just to avoid that whole thing, what you can do is, well, make a table first, or just make a list of the variables that you're defining. And you want to make sure that it represents a quantity. And what I mean by this is that it makes sense that it's not just a concept, that we're really thinking about, can you put a number on it? Like, can you say, if you define a variable v, can it equal a number? Okay, v equals 32, or something of that sort. Oftentimes, you know, with some word problems, you might get some phrases that may be kind of ambiguous, and really what they probably mean is more than just a single variable or something like that. Make sure it breaks down into sufficiently small parts. And when you're defining variables, include the units of measure. This always is really very helpful, because in the real world you're not going to get conveniently all the units of measure in the same units. Like you know, lengths. Lengths are in inches, feet, meters, microns. You know, a lot of different things, and you might get problems with mixed units, and so you'll have to settle on what unit do you want to use. And so if you're going to settle on centimeters for your length, all your numbers should be translated into centimeters. Now this perhaps sounds a little obvious at first, but you remember the Hubble Space Telescope, I guess, is getting towards the end of its life, but it was sent up in the early 90s into space, and they were always bragging about how carefully this mirror was made and how great of a telescope this thing was going to be. They launched it, and when they started it up, the guy who was operating the telescope recognized that they had something called spherical aberration. That means the outside of the mirror didn't focus to the same spot that the inside of the mirror focuses. And so they couldn't figure out why. Initially, you know, they didn't expect anything. And so it took them about 3 weeks to figure it out, but they finally got to one engineer's work who mixed units. He mixed a formula that was in inches for centimeters, or vice versa. I don't remember which the way it was, but that was a $100 million mistake because he didn't carefully write his units out. And this is from an engineering standpoint, that's a colossal failure. You know, I mean, that's a lot of money to send a space shuttle up to service this thing, and they never really did get rid of all the little aberrations because of it. And so, you know, I really want to emphasize writing variable definitions with units is something that is crucially important in any kind of work. Okay, so here's some ways to have some definitions of variables. And so, you know, like B is a good one for Bill's age in years, or D is the number of dimes. Now, the number of something doesn't have a unit to it. The value of dimes now does. That's in dollars, or it's in cents, or whatever. You have lengths in inches, and area in square inches, and things of that sort. So these all would be perfectly good definitions to write when you're translating expressions into language expressions into algebraic expressions. And oftentimes, you know, when you're looking at definitions like this, the number of dimes and the value of dimes, you know, if I say in my pocket I have 37 cents in nickels, dimes, and pennies, and I have, let's say, seven coins. You've seen those kinds of word problems before. Those are sometimes difficult to wrap your head around unless you start doing this, where you say, okay, this is the number of dimes and the value of dimes. And so you take D times 10 cents will be the value of dimes. You know, you can start building up your phrases by having careful definitions of your variables. And almost always when you are struggling to set up some equations, you can do better by first defining those variables. So here's some examples of poor variable definitions. If you just start using X, don't just start using X. Or if you say B is bill or D is dimes, well, dimes is that value of dimes or number of dimes. And so, you know, be specific about what you're referring to. Okay, so your book spends some time talking about constructing models. And so what this model often is just kind of a mix between algebraic signs and words that kind of represent the quantities. Like, here's a number of dimes times the value of dimes plus the number of quarters times the value of quarters. Well, that will give you the total value of what you have in coins. And so, you know, when you have a problem that says this equals, you know, this particular variable, writing an ordinary language model like this helps you. And then what you can do is you can go through and define your variables from here. You can say, okay, I'm going to need D as the number of dimes, 0.1 is the value of dimes, N is the number of nickels, and then, you know, you go on from there. Here I'm mixing my example. I have nickels and not quarters, but nevertheless, you should see the point where I have both the variables and also the constants that I know with some definition. Because what my goal is to write an expression that comes out of my ordinary language model. And so we can rewrite that. It'd be interesting to see. I guess I use nickels instead of quarters. But you get, you know, this expression, and this, you know, looks like a fairly ordinary algebraic expression, and for the time being then you can forget about what D's and N's are, but you have something to manipulate. And so this is really the first 3 steps in what you do when you're solving a word problem. That we write a model or draw a picture or make some type of gather some type of information around what you're reading. The second step always is to define variables. Third step then is to make your equations. All right. Now, one of the things that you'll find when I'm grading tests, word problems. Everybody hates those, and traditionally people don't do very well on them if they're not, if they're not really secure with that. Is that you will get most of the points of the problem by doing these 3 steps. And let's say you get this wrong, at least you did the step, okay? Sometimes coming up with this ordinary language model is kind of hard or so. More often than not, it involves a diagram. So draw a careful diagram or write, some phrases that fit together. Define your variable and start making your equations. And then if you're successful at writing the equations, then the answer comes out pretty easily. But this is really, those 3 steps are the hard work of the problems, and you'll get most of the points of the problem if you do those 3 steps. And this doesn't assume that you're going to get this particular equation right. Okay, so those 3 steps, and there's going to be 2 more. The 2 are easy. The next one is solve your equations, and then the last one is answer the question. Okay, I don't know, am I looking for D, or am I looking for N, or am I looking for the total number of coins? The rereading the question and then answering it in a natural language really helps you translate back from all your symbols into something that has some meaning.